Yep. Okay, Paolo. Yeah.
Yeah, I just wanted to make sure that so for the pole zero, I'm not sure if I'm using the correct code for it because what I found
Just
online
show
is
me the code. Can you share your
yes.
screen?
Yeah, 1 second. Um, okay. Okay. So this is what I got till now.
Okay, I can see
So
now.
I get the same as hers, but mine is
Mm,
not showing it on the limit. Well, I think that's what you're supposed to get, right?
yeah, yes.
For
You have 180 to 220
yeah. Mm-hmm.
preserving these frequencies, and the remaining frequencies are attenuated. So the
Yes.
filter has been designed correctly.
Okay. But then for I saw online that this is what you use for the pulse zero is this command here. But I didn't know what to do with the system. So for the system, do I need to do a transfer function of the num and then that we got,
Okay,
or what, or
let me use what code I used. If I look at what I did, I used Z plane of num and then, and automatically it gives me zero and poles. So just instead of PZ map, just write down Z plane.
oh,
So maybe comment this PZ map,
okay.
and let's use this
But
command.
do we need to use do we need to make the transfer function, or there is no
No,
need to
just
do it?
directly using num and then.
Oh,
So
okay.
you can use Z plane of num and then.
Of num and them, is that how you?
And maybe give it a try to see if it is working.
Oh, okay.
Yes. Okay. Yeah.
Oh, that was it then.
I
Oh,
haven't
okay.
used the PZ map, so I'm not sure exactly what should be the input or
Yeah, because
output.
I wrote on Google how to plot pole zero because I had no idea, of course. But then and it showed me this. I didn't know you had
But
to use.
something that is very important, I wanted you all to figure out, is how putting a lot of poles in the area that in the frequencies that we would like to keep make our filter. So in reality, in this filter, in the range of 180 to 220 hertz, we have a lot of poles. And actually, these poles keep the frequency response being one at the passband range. So I asked you to plot zeros and poles to better understand how putting
Hmm.
zeros and poles in different location of Z planes uh, lead us leads us to have the filter that we are hoping to have.
Okay,
Yep.
but so this is just basically what is this telling us? How the filter is like?
So it
This ones
shows
and zeros.
us, yes, if
Yeah.
you have one zero in zero, omega equals to zero, and you have one zero in omega equals to pi, and both of them are in a unit circle. So it means that the frequency response in zero and pi is zero. Okay,
Yeah.
and you have bunch of uh, poles very close to each other in a specific frequency band.
Hmm.
That plane, we start from, in unit circuit, we start from z equals 1, omega equals to 0, and we move forward up to omega equals to pi. When we
Okay.
are close to 0, our frequency response gets attenuated, and when we are close to poles, the frequency response there is going to have a peak. So now your case, in
Hmm.
in omega equals to 0, you have a 0. So the frequency response is 0. You move forward, you get far from the 0 and close to poles. So your
Hmm.
frequency response increases. When you
Yeah.
get very close to poles, you're going to have peaks. And when you get far from the pole, the frequency response gets decreased until you get to pi, which is you have exactly a 0. So the
Hmm.
frequency response gets exactly 0.
Okay.
We are practicing using Z-plane to somehow design filters this Friday.
Okay. So, all right.
Okay. But the main point is that when we are in a unit circle, when we are close to zero, we have attenuation in frequency response. When we get close to poles, we have increase in frequency response.
Okay. Makes sense.
Perfect.
All right. Well, I mean,
Okay, great.
I could ask directly about question 2 that I have that I got confused.
Anybody else asking any
Yeah,
questions
I guess
about
someone else should
problem
go.
one? Yeah. Oh,
Yeah.
okay, that's great. But nobody is volunteer yet. Who
Oh,
wants
okay.
to be the next? If not, Paulo, let's go for the second question.
Oh, okay. That's fine. Can you see my screen yet?
Not yet. There should be a few
No.
seconds delay, but if you share again your
Okay.
screen.
Now, can you see it?
Yes, it's coming.
Okay. So for this one, obviously I just don't want the answer. I just want to like a hint to know what needs to be done here. Cause let me put it like this. So yeah.
So I gave you some samples. So I
Yeah.
would like you to plot your signal in time domain before filtering and after filtering. And
Yes.
also, what I asked you to plot, I wanted to plot signal in time domain before and after filtering, and also plot magnitude and phase of the filter. Okay, so plot magnitude and phase of the filter, see if it is a high pass filter, if it is a low pass filter, what type of filter it is, okay? And thereafter, look at your signal in time domain. See which parts have in time domain has been removed. Are there low frequencies or for high frequencies? Somehow I would like to get better understanding if we have a high pass, which parts of the signal we expect to be removed or gets smoother. Which part, if we have low pass, which parts of the signal we expect to be removed. Yep.
Okay.
So
So if,
maybe plot
yeah.
them and thereafter we can discuss together.
Okay. I'll try to do that then.
Yeah.
I'm his teammate, and we're doing the report together. So is it fine if I show you and see if you tell me it's right, so he knows what he's
Yeah,
looking for as well?
that's great. Yep. Why not?
Okay. How do I share my screen? Okay, share contact. Share screen. Here we go. No. Right. I cannot allow it.
Maybe
Okay.
Ivan.
Now it says no.
Yeah.
Can you see
There
it?
are some delays in the system. Yes, I can.
Okay. So has he shown you exercise 1 already?
Yes.
Okay. Well, is this? Oh, something's wrong.
So you're running the exercise 1.
What was it wrong? The cutoff frequencies will give me the intervals 0 and 1. Yes, they should be. 0. Oh, okay, yeah. Right, that was. There you go. That should be it. Right. I'm not sure about the pole set map. Why isn't this showing?
Okay. What I asked you for
Right.
question 1, please, instead of using PZ map, use the command Z-plane, because Z-plane can directly get num and then and give you the Z-plane. So let me write it down
Right.
in the message bar so everybody can see. So for
Oh,
problem 1.
you can't see the actual figures, can't you?
No, I cannot see yet.
Oh
Sorry.
my God.
You need to share the entire screen,
Yeah.
not just an application.
Nah. Right. There you go. Oh. So is this the filter that you were looking for?
This is the pole and zero. Exactly, correct.
So that's the filter, okay? And then I'll change the pole and
So
0.
when you see, so to all the students who are in the room, just to give them a hint. For problem 1, when you look at the magnitude of your filter, you need to see that from 180 to 220, this is the frequency that has been preserved. So it's your passband frequency. The remaining frequencies, you need to see that they are getting attenuated. And of course, Peter. And about the Z-plane, why I ask you to plot Z-plane? Because I wanted you to get better understanding how putting zeros and poles in different parts of the Z-plane can make the filter. The thumbs up rule. When we are close to 0, the frequency gets attenuated. When we get far from the 0 and we get close to poles, we are going to have peaks. The frequency response, the magnitude of the frequency response gets increased. So here in Z-plane, in the unit circle, on the unit circle. So we start moving. So we start from omega equals to 0. So now omega is 0. So we have a 0. So a frequency response is 0. When we move forward in the Z plane, we get far from the 0 and we get close to the poles. So our frequency response gets increased. And when we get far from the poles and we get close to zeros, again we have decrease in frequency response. Yeah. Okay. So shall I go to the next one?
Yeah. I don't know if it's just me or if anyone can just like say yes or no in the chat. But sometimes your microphone gets very muffled.
Okay, so I turn off.
Maybe it's just me.
Can you see also that my microphone gets faded? If it is the case, I turn off my camera to make sure that I have a high quality internet. Hopefully it's better now. Yes?
Yeah. People are getting the microphone
Yes,
also.
yes, it goes in and out. I don't know why my internet connection is like this today. But I turn off my camera to make sure that I have a better quality.
It still happens, but it's fine. It's fine.
Oh, sorry. Hopefully, I don't know what to do.
Right.
But
should I show exercise 2 and see if?
But one more thing. If you want to be the next person, please write down your name on the chat box. Okay? So
Okay.
yes, I mean the other people. So
Yeah.
Let's go for the second question. Yes.
Okay. So I'll share my screen again and. Right. Okay, so MATLAB. So it asks for the time domain before and after filtering, and then for the magnitude of the filter, right? So, right. So this would be before, like unfiltered. This is filtered, and is this the filter?
Yes.
Yeah. Okay. So
all correct. But what I would like you to explain to me, look at the pulse. You have a pulse. And if you maybe plot unfiltered data and filtered data together.
If I were to plot them both at the same time?
Yes.
Okay. Do you want me to do that live or do you?
Maybe you can do it later. But what I hope to see in edges, when we have a sharp change, for example, from 0 to 1, here we have high frequencies because the change is quick. Then we have our signal always 0 or 1. There is not that much change. So this part of the signal contains mostly low frequencies. Again, when we drop from 1 to 0, we have a sharp change. So mostly our signal has high frequencies in these parts. And as you can see, what type of filter do you have now?
This is a high pass filter.
So we expect to see low frequencies getting attenuated and high frequencies being preserved. So as you can see, still you have some sharp edges in your signal after filtering, but the parts that was 1, they have been removed. So the parts that the pulse is 1, it has low frequency. But when we have changed from 0 to 1, we have high frequencies and they are still in the plot.
Yeah, okay, that makes sense. Yeah.
Perfect.
Right. I haven't been able to do more, so that's all I have. So
I'm here. I answered the other questions, and thereafter we can get back to you, Ivan. Okay. Perfect.
Okay, well, I'm done. I'll let someone else like present, and I don't think I have any more questions.
Thank you so much. Thank you.
Yeah, thank you so much.
So, Kriti, I think you are the second. You're next.
Hello, do you hear me? Do you hear
Yes,
me?
I can hear you.
Okay, so I'm gonna share my screen to you in a bit. Share screen. MATLAB. So, do you see my MATLAB screen now?
Yes, it is coming.
Oh, okay. So, I've done so far that everything is the same at Ivan and everyone, I guess. But
That's correct.
I've done the question 3 already.
Okay,
So,
let's go.
so
What you find?
So I find that the the order is here. So the order is gonna be the butter, the Sherby one, Sherby two, and elliptical. So is that what is
Let
supposed to be or
me,
not?
let me check my answers.
Oh,
I
oh,
did
okay.
it many weeks ago, so I need to remember the answers. So can you repeat what you got for Butterworth filter? What was
I
the
got
order of
I got
Butterworth?
I got 22 and WC is 0.2 or 63. Is here.
So the order of Butterworth is 22. What is the
Yes.
order of Chebyshev type 1 and type 2?
Is both 9.
Correct. And what is the order of elliptic filter?
Is 5.
That's they are absolutely correct. So just to you and all other students, the main reason that I gave this problem to you to get better understanding about the design of the filters. We are going to discuss this on Friday. Usually having the same features, same specification, Butterworth has the highest order and elliptic filter they have the lowest order. So with the same specification, if you go with elliptic filter, your filter has a lower order, which is good, means computationally is going to be less expensive. But the good thing about Butterworth usually doesn't have rips in stop band and pass band. But elliptic filter, it has rips in both pass band and stop bands. So these are uh, important things that you need to consider when you want to choose your IIR filter. Shall you go with Butterworth? Shall you go with elliptic? Shall you go with Chebyshev filter? So I will discuss with you how they look like, what are their specifications on Friday. But something that you learned from this problem number 3, is that if you go ahead with the same specifications, Butterworth has the highest order and elliptic has the lowest order. So if computational time is important for you, go with elliptic. Okay,
Okay.
perfect.
So I just want you to check the
That's good.
the
Yeah,
graph.
I'm here. I'm here to check to make sure that you did it correctly.
Okay, for the first one. So I guess it's correct, right?
Yes.
Okay, that's the first one. That's the second one.
Oh,
Do
you
you see
mean the
it?
first question is correct or not?
Yeah.
Uh,
You seen
if
it?
if you show me the plots, it's easier for me to say. Can you show me the plots? Hello. I'm not sure if Kriti is still here. Okay, yeah,
So
I saw it.
so the plot for the first one. So
Yes,
that's
that's correct. Yep.
and that's the set
And
plane.
the second one is also correct.
Okay, so that's
Great.
the second question.
Mhm.
The the phase and magnitude, right?
That's all correct.
Okay, so this is the last bit. The the both one. Is correct, right?
Yes, yes, yes.
Okay.
So
So
I repeat again to all of you, but I'm hoping you discuss for question two. Okay. For your question two, you have a pulse. If you can look at your signal in time domain, what you see, for example, there are some changes from 0 to 1. When we have changes, sharp change from 0 to 1, the signal changes so quick. So we mostly have high frequencies. When we have changes from 1 to 0, we have a quick change, so your signal has high frequencies. When your signal is constant, 1 or 0, these parts of the signal mostly contain low frequencies. Now your filter in question 2 is a high pass filter. So you expect low frequencies to be attenuated and high frequencies to be kept. And as you see in time domain, the high frequencies is still kept. Yes? So let me see who is next. Chelsea, is going to be the next person. So what I would like to remind you all again, if you want to ask a question, please write down your name so we answer the questions in order. And Chelsea is the next person. Chelsea, can you hear me?
Hi, yeah, I didn't have a question though. Everything's been answered for
Okay,
me.
answered.
That's
Okay, perfect. So Hiba,
Thank you.
you're welcome. Hiba, still, do you have any questions from problem 1 to 3?
Hi, I just have a little question. Let me share my screen.
Oh, sure.
I think share application screen. Can you see my screen?
It seems, yes, it's coming.
Okay. So I have a question in the writing of this function, the frequency z, or any other function, because I noticed in your notes, for example, this one here, you use 512 and you put 4000. I'm assuming is the sampling frequency.
Yes, exactly.
But I don't know why you put 512, and I'm not sure what to put for my answer.
512 means how many points I would like to have my frequency response.
Okay.
To here, I wanted to have my frequency response having 512 points. And I can say, for example, do you remember FFT? So we gave FFT of, for example, our signal, and we gave it how many points to use to calculate FFT?
Yes.
This is the same. We say Frex how many calculate our frequency response using how many points.
Okay.
So higher number to have a better resolution.
Ah, so it doesn't have to be exactly the same number as 0 to 500. So it can be more. We can make it more.
Yes, you can go for 512. You can go for 1000.
Okay. Okay. That's great.
If you give a very high number, it takes some time for MATLAB to calculate it.
Yes.
But this is the matter, how you can increase the resolution of the visualization by increasing the number.
Okay. Okay. That's great.
But
Thank you very much.
it's something that you choose.
Yeah. Yeah. I was confused because I didn't know. Thank you
I
very
don't know.
much.
It's good to know. I didn't write it down here, so it's good to
Oh, no,
clarify.
it's fine. It's fine. Thank you so much. Thank you.
You're welcome. So Hiba, is all that you wanted to ask?
Yeah, I think my questions have been answered by other people who asked them, so I think it's fine now.
Perfect.
Thank you
So
so much.
you're welcome. So I see the next person is Lokman. So Lokman, do you still have any questions related to problem 1 to 3?
Yeah, hi, Dr. Mahnaz. I've got questions related to problem 2 and problem 5, but I don't know how to share my screen.
So let's go for problem 2 first. And would you like me to tell you how to share your screen?
I think found it.
Yes, you're doing great.
Okay. First of all, about problem 2. So this is a change I made to the file I had sent you earlier. You said
Now I
magnitude
see what I
response and
was.
phase response weren't correct.
So before Lokman, just would you please give me a second? If for other people, if you can mute your microphone, that would be great because I hear the echo of my own voice. Okay, so if you're not talking, please mute your mic. So Stefan, if, maybe I can mute your mic. Okay, perfect. Now I don't hear myself. So, Lokman, let's continue. Lokman, I cannot hear you.
Yeah, I think
Okay,
you
now
muted
I
me
can.
along with
Okay,
everybody else.
perfect.
Okay. Yeah. So is magnitude response and phase response of task
Exactly.
2 correct now?
Yeah. So what type of filter is it?
It's a high pass filter.
Yeah. And of course, it's not a very nice, it's not very close to ideal filter at all because the order of the filter is 1.
Yeah.
So if we increase the order of filter, the filter gets closer to an ideal filter. But this
Okay.
is
Yeah.
only a filter with the order of 1.
Yeah. Okay. Thank you.
You're welcome.
And then, yeah, earlier it was different because I couldn't plot it using just the normal function, so I viewed it using FV tool.
Okay, yeah. Now it's correct. It's what I was hoping to see.
Yeah. And with problem 5, I couldn't get the random code running.
Okay,
So in this
because we
diagram,
don't have many people waiting, we have only Paulo. So let's go for, it's okay to go for question 5 now. So priority is with problem 1 to 3. But if we don't have a lot of people waiting, we can go for problem 4 and 5. So your question is about problem 5, yes?
yes, I couldn't get this code to run.
Okay, the ECG one, yes?
Yes.
I noticed in old versions of MATLAB, the ECG function, which artificially generates an ECG file, is available, but in the newer versions, this ECG file is not available. So I put the function in on Blackboard. So
Okay.
please download that function from Blackboard.
And try it with that?
Yes.
Okay, yeah, I'll do
Let
that.
me know if it works.
I think that's why it wasn't working. So I was getting.
A couple of your friends sent me an email that it doesn't work in their MATLAB, so I noticed that it seems my MATLAB is version 2015 and it's available, but it seems they removed it in the old versions.
Yeah, I see. Okay. Okay, thank you. I think then that'll
Just
be
download it and write it down for me if it is working well.
Okay. Okay. Yes.
Perfect.
Yeah. Yeah. Thank you.
You're welcome. I think the next person is Paulo. Am I right, Paulo?
Yeah, I'm here. I'm here.
So, Paulo, sorry, before you start,
Yes.
just to tell your friends, if you have any questions, please write down your name and I make sure that I answer the questions in order. And because it seems that there are not that many people asking questions about problem 1 to 3, we can move to problem 4 and 5 also. So now, if you have any questions on problem 4 and 5, it's okay. Just write down your name. So Paulo, yeah, how can I help you?
Yeah, so on question 2, I just wanted to make sure of something. Like here. Okay, what I get is this.
So it's about question 2, yes?
Yes, okay. So I think that's what's supposed to get, like I haven't got before. But I want to understand something here. I think someone was talking about this before. What numbers are you supposed to use? Because here, for example, this is FS. Just chose a random number. Like I don't know which number to use. Are you supposed to use a high number?
Okay,
Or
that's a good question. X is a function that visualizes for you the frequency response. And similar to FFT, you can tell the function you would like to have frequency response using how many samples. Yeah? So to me, okay, your Fs is 400 hertz, yes?
Yeah.
And if you go for 200, it means that you have 200 samples. So, and it plots the frequency response between 0 to half of sampling rate, yes?
Yes.
So it means that frequencies between 0 to 200 hertz is going to plot it using 200 samples. So you are going to have one sample per hertz.
Hertz.
So maybe
Yes.
it's better to increase the resolution to maybe 600 or 800, sorry, 600, 800 to have 3-4 points per 1 hertz. So you increase the resolution. I'll go for 1000, for example, to improve
So
the
if
resolution.
you go 1000, it's gonna be from 0 to 200, and it's gonna be
Using 1000
okay.
samples. So every 0.2 hertz, you are going to have one sample.
Oh no, it should be this one.
Yes. So of course, this is a Butterworth filter. It doesn't have a lot of ripples, but generally, a rule that you can consider is that look at the frequency range that you have from 0 to half of sampling rate and estimate what would be a good resolution for you to plot the filter. I would say consider 4 or 5 points per hertz.
Sorry, can you repeat that last part?
So I consider 4 or 5 points, 4 or 5 samples per hertz.
Yes.
Yeah.
Yes.
Okay,
Okay.
perfect.
So that's just a matter of how much resolution you want to have on your display, and that's it.
Exactly.
Or is there a minimum sampling rate that you have to have, or it doesn't matter which sampling rate you
No,
have?
it's what you choose. You choose what would be the resolution that you
Okay.
prefer to have. And of course, if you increase the number of samples, the computational time will increase.
Okay, makes sense.
Mhm.
All right. Well, I think that's for this part, right? Well, that's why you're supposed to get just these three. That's the
Perfect. Yes,
unfiltered.
exactly.
That's the
And you need to
filtered, and then
explain to me that you expect to see in edges of the pulse high frequencies, mostly high frequencies, and in the other parts low frequency. And you can see also the high frequencies in time domain signal is preserved, and low frequencies have been removed.
okay. Here you can, I know this is a high pass filter because you can tell, but how do you analyze that it's a high pass filter to see if you have
Okay.
the same?
This is in decibel, yes?
Mhm.
So if I look at the magnitude of the signal, the part that is 0 decibel means the magnitude is 1. And the parts that the magnitude is negative means that we have attenuation. Because if you convert the magnitude to decibel, 20 log of magnitude is the decibel of the signal. So when we have, for example, minus something, means that the magnitude is very small. Mhm.
Okay, so it's because the magnitude is going to be negative on when it's close to
Low
zero.
frequencies, yes. And in high frequencies, the magnitude is very close to 0. 0 decibel means it's close to 1.
Yeah. Okay, makes sense.
But Paolo, this is a order 1 filter. It's not close to ideal filter at all. You know, it's a
How do you
very,
know if a first an order one?
okay, that's good. Go to uh, the part that you look at the Nomden butter 1 cutoff high, the script that you used. And actually,
Yeah.
I gave it to you. I gave you,
Oh yeah. Here.
so
Okay.
this
Yeah.
1 is the order of the filter. Yes?
Oh, okay. Okay. So if you change it to like 8, it's gonna give you a
Just change it
more.
to 8 to see what it gives.
Oh, okay.
Okay.
Very different. Yeah.
transition is sharper.
Yeah.
It's closer to,
Okay.
and yeah,
All right. Makes
that's
sense.
good. That's good to try. Perfect. Well done. It's
Okay.
how we learn, you know. Just give it a try to see how it changes the output, the frequency. Yeah, perfect.
All right.
Paulo, any questions
Yeah.
for problem 4 and 5?
No. I'm just gonna try to do problem 3. I haven't done
Yeah,
it yet.
just go ahead, take your time, do your
Okay.
part. Uh,
Okay.
I don't know why the quality of my voice is not good. I just, if there are no questions, just give me 1 minute. I go check all my devices. It seems one of my devices is just downloading something or uploading something on the internet. So I turn off those devices to make sure that I'm going to have a better internet quality. Okay?
Okay, that's fine. Thank you.
Okay, thank you so much. Thank you. Maybe I stop recording also.